Hello and welcome to this session on programming techniques. By now, you would be familiar with the 8085 instructions. In this session, we shall use some of these instructions to write programs for time delays, and counters. We shall also discuss some modular programming techniques. Many applications require time delays. Let's look at a live shot of a traffic light where the red light glows for 30 seconds, the yellow for 5, and the green for 25 in sequence. These time delays can be introduced by executing instructions in the microprocessor. Can you guess how many instructions you would need to execute for a delay of 1 second? Many thousands, because practically the execution time for various instructions is of the order of a few microseconds. This is how we do it. The practical approach is to load an 8-bit or a 16-bit register called the delay or count register with a programmed value called the delay or count value. And then decrement this register till it is 0 through this loop. This loop is executed for all non-zero values of this register. As soon as the register contents reaches 0, the loop is terminated. Can you now write a program for a 1 millisecond delay or a 1 second delay? You can, if you know the microprocessor clock frequency and relate it with the instructions being executed in this loop. You can refer the microprocessor instruction set and get the T states, which is basically the number of clock cycles that the instruction takes to execute. You can then sum up the total T states of the instructions in this loop and multiply it by the microprocessor clock time period. The microprocessor clock time period T is inverse of the clock frequency. For a 1 megahertz clock frequency, 1 T state would be equal to 1 microsecond. For a 2 megahertz clock frequency, 1 T state would be equal to half a microsecond. Therefore, instructions totaling 24 T states would take 24 microseconds to execute if the clock frequency is 1 megahertz, but would take only 12 microseconds to execute if the clock frequency is 2 megahertz. Let's now develop a program for a time delay using an 8-bit register. Here, register C is the 8-bit register which is loaded with the desired count value to give a 1.4 millisecond delay. We shall come back on what this value should be later. Then, register C is decremented until C is 0 through a loop to give the desired delay. The instructions being executed in the loop are decrement C and jump on non-zero to loop back. The execution time of these loop instructions can be referred from the instruction set and are 4 plus 10 equal to 14 T states. For a 1 megahertz system clock frequency, 1 T state would take 1 microsecond. 14 T states would require 14 microseconds. If n is the number of times loop has to execute to give 1.4 millisecond delay, then the value of n would be 100. The microprocessor registers are usually programmed in hexadecimal values. The hex value of 100 is 64, which is loaded initially in the C register by the move immediate C instruction. An 8-bit delay register is used if the delay is of the order of a few milliseconds, because the maximum value that can be represented by this 8-bit number is 255. For delays in seconds, a 16-bit register or a register pair is used. Let us look how the program would look like in this case. The register pair selected here is BC, which is decremented till it is 0. The maximum counts it can be decremented is 64K. Note the instructions being executed in the loop this time. Can you guess why we need the move C to accumulator and or B with accumulator instructions, which is basically ORing B and C registers? This is because the decrement register pair instruction does not affect any flags, but the decrement register in the earlier example does. The ORing operation ensures that both B and C have reached 0 and sets the 0 flag if they have. We now need to calculate the execution time or T states of the loop. Here, the total T states are 24. For a clock frequency of 2 megahertz, the loop execution time would be 12 microseconds. For a 100 millisecond delay, this loop has to be executed 8,333 times. The hexadecimal equivalent is 208D. The B register pair is loaded with this value to give a delay of 100 milliseconds for a system clock frequency of 2 MHz. We have discussed simple methods to write programs for time delays. Can you guess what would be the accuracy of such delays? Practically a few microseconds off. This is because we have not taken into account 1. Loops can be executed only for integer number of times. 2. The execution time of the initialize delay register instruction move immediate to C or load immediate P. 3. The finer programming aspects of the jump or non-zero instruction, which takes 10 T states when the condition fails, but only 7 when the condition is 0. The last loop execution would therefore execute less by 3 T states. For most of the applications like traffic lights, washing machines, microwave oven, etc., where the required delay is of the order of a few seconds or even minutes, this error in delay is insignificant, and you may not have to bother about complicated programming. But in applications like baud rate generation for serial transfer, you may have to. Here, you can program the delay or count value which comes as close to the required delay. The balance of the delay is partly shared by the initialization instructions and partly by adding NOP instructions. Let us develop a flowchart for a counter with a specified delay, say 1 second, between its counts. The counter is first initialized to the start value, which now denotes the present value of the counter. This value is sent to display. The required delay of 1 second is introduced here. The counter is incremented or decremented for the next count state. The counter is checked for the count over condition. All valid states of the counter are sent to display and operation repeated. Once the count over condition is reached, the flow goes back to the beginning where the counter is again loaded with the start value. Let us now write a program for a 0 to 9 up counter with a 1 second delay between its counts. Let B register be the counter. which is initialized to 0 as the counter starts its counting from 0. The B register is sent to display, followed by a delay of 1 second. The register B is then incremented for the next count. The count over value here is 0A, which is equivalent to decimal value 10. For values 0 to 9, the flow goes back to display the count value. As soon as the count value reaches 0A, control is transferred to the beginning. The display in this case is connected to port 01 and is sent through the out instruction. The move B to accumulator preceding it is required because for the first time B register is initialized with 0 but is not transferred to accumulator for the out instruction which sends it to display. Lastly, we require to adjust the delay count for 1 second. Here, we use a register pair HL as the required delay is very large. As discussed in the earlier example of 16-bit register delay, the loop delay takes 24 T states to execute. The highlighted instructions get executed in the counter loop denoted by label DIS. The instructions out, load immediate, increment B, move B to accumulator, compare immediate, and jump on non-zero to DIS are the instructions that get executed whenever the count value increments, and they total to 45 T states. This time needs to be considered for calculation if we require sufficiently accurate counts. To sum up the timings, for a clock frequency of 1 MHz, the loop delay takes 24 microseconds with an initial time of 45 microseconds. Therefore, the 1 second delay here is 45 microseconds plus time for n, the number of times loop delay executes. The value of n through calculation yields 41,664. The corresponding hex value is A2C0, which is loaded through load immediate instruction preceding the loop delay. In this example, we had the next count step towards the end in this loop. Let us look at an alternate flow chart where the next count step is towards the beginning in this loop. The counter here is initialized to a count value which is one previous to the start count. The count goes to the next state and is then displayed through an output port. The required delay is introduced and the count value is checked for the last count state. If the last count has not reached, the flow is transferred back to the next count and loop repeated. Once the last count is reached, the flow is transferred to the beginning. We have discussed two flow charts of a counter with delay doing the same thing. Can you tell what's the difference between the two? In the former case, the counter was initialized with the first count value and later incremented. Thus, the terminating check is done with the count over condition. In the later case, the terminating check is carried out for the last count value. Let us analyze the program for a 9 to 0 down counter with 1 second delay using the later flowchart. Here, B register is the counter and HL register pair the delay register. As the decrement B operation is carried out before display, we have to load the counter with 0A, which is equivalent to decimal 10. The counting, display and delay for valid counts 9 to 0 are performed in this inner loop. The check for last count is performed, which is 0 in this case, and then control is transferred to the beginning to repeat the desired count sequence. Note the instructions in the main count loop this time. Now, the T states outside loop delay are 49 instead of 45 in the earlier example. In real-world applications of microprocessor, the programming or software runs into many kilobytes of instruction code, which seems quite complex. How does the software designer manage the complexity in such programs? He starts from the top with the entire software requirements. Then the overall requirements is divided into major system blocks and is further divided into smaller functional modules whose complexity is now manageable. This methodology of software development is called the top-down design approach and is equally applicable for hardware designs. The next step is to define how these modules interface with each other. In software, it is called parameter passing. In hardware, it is through signals. While implementing the bottom-up strategy is adopted. Where the lowest level modules are coded first. It's quite likely that after this analysis, many functional modules may require similar tasks to be performed. These tasks are called subroutines. Let us now analyze the traffic light problem using this kind of software design approach. We first develop a flowchart for a problem by identifying and sequencing the various tasks. First, red light is turned on. All other lights are off. This status is maintained for 30 seconds by a delay. Then yellow is turned on. Both red and green are off. This status is maintained for 5 seconds by a delay. Then green is turned on. Both red and yellow are off. This status is maintained for 25 seconds. Then the sequence is repeated by transferring control to the beginning. After breaking up the problem into 6 different blocks, we find that a programmable delay in seconds is required by 3 modules. This can easily be implemented by a delay subroutine, which accepts a parameter number of seconds. One of the internal 8-bit registers can be selected to pass the number of seconds parameter, say register B. The next step is to control the lights. This is done through an output port which is usually latched. Here we have selected port 01 as the output port. The lights are connected to the lower 3 bits of this port. Sending a logic 1 on the corresponding bits would turn on the light, and logic 0 would turn it off. Let us now implement this flowchart by coding the instructions in the various blocks of the main program. To turn on the red light, we need to send a logic high to the bit number D0 at port 01. As the other lights are to be in the off state, the other bits D1 to D7 are at 0 level. The data pattern to be sent is therefore 01, which is first loaded with a move immediate to accumulator instruction and sent to port 01 through the out instruction. The delay routine is then called by first initializing register B with 1E for 30 seconds. This parameter will be used by the delay subroutine to give a 30 seconds delay. As the display is latched, the status of lights is maintained, that is, red on and others off. After this, the yellow light is turned on by sending data 02 to port 01. 02 represents the bit pattern, D1 being logic 1 and all other bits 0. This would turn on the yellow light and red and green would be off. The register B is then initialized by 05 for the delay counter. Green is then turned on by sending data 04 to port 01, which turns on the green light and other lights are off. A delay of 25 seconds is introduced by programming register B with 19, which is the hexadecimal value for 25. This is the flowchart for the seconds delay routine. The number of seconds parameter is passed in the B register. The register pair is used here to give 1 second delay and is loaded with A2C0 for a 1 MHz clock frequency. The outermost loop is the down counting of the register till it is 0. In the traffic light example, internal register was used to pass a parameter. What do you do if you have a large number of parameters? In this case, it is convenient to assign a memory block to the data. Either the calling routine knows about this reserved data block, or you may pass the start address and the number of data items through internal registers. You may also use stack to pass parameters. For retrieving parameters from stack, you have to first pop the return address the parameters in the reverse order and then push back the return address. With this, we end up this session.